There is something traveling toward you right now that has no weight, no mass, and no memory of the journey it just completed. It does not age. It does not tire. And yet, it carries oldest information in the universe pressed gently against its surface, arriving at your eye the way a letter arrives after the writer has already gone. Light is not simply what lets you see. It is the oldest language the universe knows how to speak, and it has been speaking, quietly, since before the Earth existed. You may never have thought of light as something that could push. It moves so softly through a room, so silently across an open field at dusk, that the idea of it exerting force seems almost too quiet to be true. And yet, light presses. It leans. Every beam that lands on a surface delivers a small, measured nudge, a force called radiation pressure, as real and physical as the weight of your hand resting gently on a table. Scientists first confirmed this in 1900, and even then, the numbers were almost too small to hold. The pressure of direct sunlight on your open palm is roughly equivalent to the weight of a single grain of pollen. It does not feel like force. It feels like warmth. And perhaps that is the most extraordinary thing of all, that something pushing against you can feel, so completely, like comfort. The warmth you feel right now, if sunlight happens to rest across your skin, is not new. It did not begin this morning. The light reaching you today began its life as energy deep inside the sun's core, where temperatures exceed 15 million degrees, and matter presses against matter with a weight beyond imagining. There, a photon is born. But it does not travel straight to you. It spends, on average, 100,000 years slowly diffusing outward through the sun's dense interior, absorbed and re-emitted countless times before it finally escapes into open space. Then, in just 8 minutes, it crosses 150 million kilometers and arrives on your skin. After a journey 100,000 years in the making, it delivers its warmth in a fraction of a second, and then it is gone. What you felt just now was that ancient. A single photon is almost impossible to hold in the imagination. It has no mass. It occupies no volume in the way a grain of sand does. It exists at the edge of what the word thing even means. And yet, this particle so small it interacts with individual electrons, knocking them free one at a time, is also the same entity that crosses the entire observable universe, 93 billion light-years from edge to edge, without slowing, without fading in a vacuum, carrying information across distances the mind cannot genuinely picture. The same physics governs both scales, the intimate collision of photon and electron, and the vast, silent crossing of intergalactic space. Scientists still find no contradiction between these two extremes, only a quiet wholeness that resists easy explanation. You live inside a universe where the smallest things and the largest things obey the same patient rules. In the open emptiness of space, light travels as fast as anything in the universe is permitted to travel. But the moment it enters something, the universe asks it to slow down. Inside glass, light moves at roughly 2/3 of its maximum speed. Inside water, it slows further still. This is not resistance in the way we usually picture it. Light is not dragging through something thick. What happens is more subtle and more strange. The electromagnetic field of the light interacts with the atoms of the medium, and the result is a measurable, reliable reduction in speed. Different wavelengths slow by different amounts, which is why a prism can separate colors. The universe has arranged things so that even the fastest thing it contains must negotiate its passage through matter. Scientists understand the mathematics precisely. The deeper reason why the universe is structured this way at all remains one of those questions the world keeps quietly to itself. Light travels forever through empty space. There is no friction in a vacuum, no resistance, no slow erosion of the beam over distance. A photon set free in the void will continue until it finds something to land on, and if the universe offered it nothing to land on, it would continue indefinitely, carrying its small cargo of energy across all of time. And yet, graphene, a material just 1 atom thick, absorbs 2.3% of all the light that passes through it. A single layer of carbon atoms, thinner than anything the eye could detect, quietly claims a measurable portion of whatever light dares to cross it. Something that can cross the universe cannot fully cross 1 atom's width of graphene without leaving part of itself behind. The universe contains things that can travel forever, and things that can stop them without even trying. Tonight, if you step outside and let your eyes adjust to the dark, some of the light you receive has been traveling longer than the Earth has existed. Our planet formed approximately 4.5 billion years ago. Many of the stars visible from Earth are far older, and their light has been moving through space since before this world had an ocean, before it had a sky, before the first molecule that would eventually lead to life had assembled itself in the warmth of ancient water. You are standing on a young planet, receiving messages from a universe that was already ancient when the Earth was born. There is no instrument required to feel this. You only need to go outside and look up, and let the age of what is touching your eyes settle over you, slowly, like something vast and gentle arriving at last. There is a question at the center of physics that has remained open for more than a century, and it concerns something you have lived with your entire life without knowing the question existed. Light behaves as a wave. It diffracts, it interferes, it spreads. And yet, light also behaves as a particle. It arrives in discrete packs, knocks electrons free one at a time, and can be counted individually by sensitive instruments. These two descriptions are not reconciled. No one has found a deeper picture that explains why light is both, or what it fundamentally is beneath both descriptions. Physicists work comfortably with the mathematics, which is precise and reliable, but the question of what light actually is, when no one is measuring it, remains honestly and quietly open. You are surrounded by something the universe has not yet fully explained to us. In ordinary experience, light is the fastest thing there is, and nothing you encounter in daily life challenges that. But in the laboratory, physicists have done something that once would have seemed impossible. They slowed light to a near standstill. Inside a Bose-Einstein condensate, a state of matter existing only a fraction of a degree above absolute zero, light has been slowed to just 17 meters per second, roughly the pace of a cyclist on a gentle slope. The photons were not stopped outright. They were absorbed and re-emitted so rapidly and so perfectly that the pulse of light moved through the condensate as though wading through something extraordinarily still. Scientists still debate the precise nature of what is happening at the quantum level during this process. Even the fastest thing in the universe, it turns out, can be coaxed into a kind of patience. The color of a thing is not stored inside that thing. A red apple does not contain redness the way it contains water or sugar. What it contains is a surface that absorbs certain wavelengths of light and reflects others, and the wavelength it reflects lands on your retina and triggers a specific response in your cone cells, and your nervous system translates that response into the experience you call red. The color lives in the transaction between the light, the surface, and you. Remove any one of those three, and the color does not exist. This means that color, one of the most intimate and immediate things you experience, is not a property of the world, but a relationship between the world and your body. Scientists can measure the wavelength precisely. What your nervous system does with it, the felt quality of red, remains one of the quieter mysteries at the edge of neuroscience. A laser beam can carry enough concentrated energy to cut through steel plate, to ignite materials at a distance, to be used as a surgical instrument of extraordinary precision. The physics that makes this possible is the same physics that governs the light arriving gently through a window on a quiet morning. The difference is not in the nature of the light, but in its organization, its density, its coherence. Sunlight is scattered across all directions and all frequencies. Laser light is gathered, aligned, focused. One feels like warmth, the other can reshape metal. The same fundamental phenomenon, the same massless particle obeying the same laws, produces both the gentlest morning in your memory and the most precise cutting tool humans have ever devised. The universe does not have different rules for the gentle and the powerful. It has one set of rules, applied with varying degrees of quiet intensity. From your perspective, time passes. You age. The light crossing a room takes a measurable fraction of a second. But from the perspective of the photon itself, something deeply strange is true. Because light travels at the universe's maximum speed, the equations of special relativity tell us that time, for a photon, does not pass at all. The moment a photon is created and the moment it is absorbed are, from the photon's reference frame, the same moment. A photon born in the heart of a distant galaxy and absorbed by your retina after a journey of billions of years experiences no duration whatsoever. It does not wait, it does not travel. For it, emission and arrival are simultaneous. Time, the thing you feel most continuously and most personally, is something the universe's fastest traveler does not experience at all. You rest inside time. Light stands forever outside it. When a massive object sits in space, the space around it curves. This was Einstein's extraordinary insight, that gravity is not a force pulling things together, but a curvature of space-time itself. And light, which always travels in the straightest possible line, simply follows that curve. This has been confirmed with extraordinary precision. Light from distant stars bends around the sun. Galaxy clusters act as lenses, distorting and magnifying the light of objects behind them. The mathematics is elegant and reliable, and yet, the quantum reason why mass curves space-time at all, why matter tells space how to bend, has not been found. General relativity and quantum mechanics each work with remarkable precision in their own domains. Where they meet, in the place where light and gravity and quantum behavior all converge, there is a silence that physics has not yet filled. A black hole does not trap light by slowing it down. Light inside a black hole's event horizon still travels at full speed, 300,000 kilometers per second, unchanged. What changes is the geometry of space itself. Inside the event horizon, every direction in space points inward. There is no direction that leads out, not because something blocks the way, but because the shape of space-time has been folded so severely that outward simply does not exist as a direction anymore. Light travels as fast as it ever did, in the straightest line available to it, and that line curves inexorably inward. It is not captured, it is simply moving through a space where escape is not a geometric possibility. The universe contains places where the very structure of direction has been quietly rearranged, and light obeys that rearrangement completely. Darkness is not a substance. It is not something that exists independently, that fills a room when the light leaves. Darkness is simply the condition of a space where light has not arrived, or has already passed through and moved on. It has no particles. It has no wave. It cannot be bottled or measured in the way light can, because there is nothing there to measure. And yet, darkness feels like something. It has texture in our experience, depth, a quality of presence that the simple absence of photons does not seem to fully account for. Scientists can measure light with extraordinary precision, counting individual photons. They can only define darkness as the lower limit of that count, the place where the instrument finds nothing. What you feel in a dark room, that quality of something surrounding you, is something the physics of light, by itself, does not explain. In approximately 1 hour, the sunlight falling on Earth delivers enough energy to meet the entire energy consumption of human civilization for a full year. This is not a projection or an approximation of the distant future. It is the reality of this afternoon, of the light arriving right now on rooftops and oceans and open fields. A single thin layer of cloud reduces this to a whisper, softening the delivery without stopping it. The sun has been making this offering for 4.5 billion years, without pause, without diminishing, without asking anything in return. What we do with that offering is a choice we are still, slowly, learning how to make. The light does not wait for the decision. It arrives, as it always has, with a patience that predates the question entirely. The speed of light was first meaningfully measured not by aiming a beam across a laboratory, but by watching the moons of Jupiter. In 1676, the Danish astronomer Ole Rømer noticed that the moon Io appeared to orbit Jupiter on a slightly different schedule depending on whether Earth was moving toward or away from Jupiter in its own orbit. The discrepancy, he realized, was caused by light taking different amounts of time to cross the varying distance between the planets. From this astronomical observation, he calculated a value remarkably close to the true speed of light, off by only about 25%, given the instruments of his time. The universe's most fundamental constant was hiding in a pattern of shadows cast by a moon most people had never thought to watch carefully. Great discoveries often live inside things we have been looking at for years. Quantum entanglement produces a correlation between two particles that appears, under certain experimental conditions, to operate without any signal passing between them, regardless of distance. When one entangled particle is measured, the other instantaneously reflects a corresponding state, even if separated by vast distance. This seems, on the surface, to violate the rule that nothing travels faster than light. But scientists have confirmed carefully that no usable information is transmitted in this process. The correlation exists, but it cannot be controlled or directed in a way that carries a message. The universe appears to permit this strange intimacy between particles, while simultaneously ensuring it cannot be used to communicate. Why the universe draws this precise line, permitting the correlation but forbidding the message, is one of the questions quantum physics leaves quietly and honestly unanswered. Living tissue produces light, not the warm glow of fever or the reflected sheen of healthy skin, but actual photons, emitted spontaneously by cells engaged in ordinary biological processes. These biophotons are extraordinarily faint, far below the threshold of human vision, but sensitive instruments can detect them. They appear to be produced during metabolic reactions, when oxygen interacts with molecules inside cells. What is less certain is whether this emission is merely a byproduct of cellular chemistry, or whether it plays some functional role in how cells communicate or regulate themselves. Research is ongoing, careful, and genuinely uncertain. Right now, as you rest, your cells are producing a faint and private light, too quiet for any eye to see, for reasons that biology has not yet fully explained. You are, in some small and measurable way, luminous. The sky has no color stored in it. The atmosphere does not hold blue the way a blueberry holds pigment. What you see when you look up on a clear day is light being scattered. Sunlight entering the atmosphere contains all visible wavelengths, but shorter wavelengths, the blues and violets, are deflected more easily by gas molecules than longer wavelengths, the reds and oranges. Blue light scatters in all directions across the sky dome, reaching your eye from every angle, while red light travels more directly through. The blue is created fresh, at this moment, by the collision of sunlight with air, and it will be created differently at sunset, when the light travels a longer path through the atmosphere and the blues scatter away before reaching you. Every sky you have ever seen was assembled on the spot, for you. just then, and has never existed in quite that way before or since. A single candle flame sends its light outward in all directions at once. As that light spreads across a growing sphere of space, its intensity weakens according to what physicists call the inverse square law, dropping to 1/4 of its strength at twice the distance, 1/9 at 3 times, and so on, across several kilometers of perfect darkness. On a clear night, the human eye, under ideal conditions, can theoretically detect just a handful of photons from that flame. The candle does not know this. It offers its light completely, in every direction, with no sense of how far any portion of it will travel, or what it will eventually touch. Some of that light will reach an eye. Some will warm a stone. Some will travel out into space and continue indefinitely. A candle's generosity, it turns out, is written in the same language as the laws of the universe. Long before anyone understood what light was made of, before the word photon existed, before any instrument could measure its speed, human beings looked at the first moment of creation and placed light there. Across cultures separated by oceans and millennia, the oldest recorded stories of how the world began share this quiet agreement. In the Hebrew tradition, light is the first thing named into existence. In Hindu cosmology, the universe emerges from a primordial sound and brightness. In the Mayan Popol Vuh, clarity precedes form. These traditions arrived at this placement not through science, but through something older, an intuition that light and origin belong together. What is striking is how contemporary physics agrees. The earliest moments of the universe were a state of pure energy and radiation, light preceding matter, photons filling the cosmos before a single atom had assembled itself. Ancient storytellers and modern cosmologists, separated by thousands of years, arrived quietly at the same beginning. Every photon carries energy, and that energy is determined entirely by one thing: its frequency. A high-frequency photon, like those in ultraviolet or gamma radiation, carries vastly more energy than a low-frequency photon in the infrared or radio range. This relationship, described by Max Planck in 1900, is expressed in a single equation so compact it fits on a single line, and yet it underpins the entire structure of quantum mechanics, the behavior of atoms, the chemistry of every molecule in your body, the design of every electronic device ever built, and the way stars eventually burn out. The energy of a photon of violet light is roughly twice that of a photon of red light. That doubling in energy is the difference between a wavelength that gently warms your skin and one that can begin to damage the molecules inside your cells. All of this is contained in one relationship between one particle and one number. Certain crystals do something to light that seems, at first encounter, almost like a conjuring trick. When a beam of light enters them, it splits, not scattered in many directions, but divided cleanly into 2 separate beams, each traveling through the crystal at a slightly different speed, each polarized at right angles to the other. This phenomenon, called birefringence, arises because the crystal's atomic structure is not the same in every direction. Light moving one way through the lattice encounters a different electromagnetic environment than light moving another way, and the crystal treats them differently, gently and precisely, the way a careful hand might separate 2 tangled threads. Iceland's spar, a form of calcite, was used by Viking navigators to locate the sun through cloud cover by exploiting this property. A crystal found on a beach, held up to a grey sky, could tell you where the sun was hiding. The world offers its instruments quietly to those who know how to look. White light is one of the most familiar things in your experience, and one of the most quietly complex. It does not represent a single wavelength or a single color. It is the simultaneous presence of every wavelength across the visible spectrum, from the deep violets near 400 nanometers to the far reds approaching 700, all arriving together, all overlapping, all present at once, in a kind of luminous agreement. When you see white, your eye is not detecting a single thing. It is receiving a conversation between wavelengths and averaging them into a sensation of wholeness. Separate those wavelengths with a prism or a raindrop, and the conversation becomes visible as distinct voices, the spectrum spreading across a surface in its familiar arc. What appears unified is always plural. What appears simple is always a gathering. White light is not the beginning of color. It is all colors, resting together before they are asked to separate. Somewhere beneath the ocean floor right now, a fiber optic cable thinner than your finger is carrying the weight of human conversation across thousands of kilometers of cold, dark water. Inside that cable, light is bouncing. Each beam strikes the inner wall of the glass fiber at an angle just steep enough that the wall reflects it completely, sending it forward without loss. In a process called total internal reflection, the light never escapes. It cannot, by the geometry of the angles involved. It simply continues, pulse after pulse, carrying encoded within its flickers the contents of phone calls, financial transactions, medical records, and messages between people who have never met. The same phenomenon that makes a diamond sparkle by trapping light inside its facets is what carries your words under the ocean. Light, confined by geometry, becomes the nervous system of a connected world. The oldest light in the universe is not coming from a star. It is coming from the sky itself, from every direction at once, a faint and ancient glow that fills the entire cosmos uniformly. Approximately 380,000 years after the Big Bang, the universe had cooled just enough for electrons to combine with protons and form the first hydrogen atoms. In that moment, for the first time, light was free to travel without being immediately absorbed. It streamed outward in all directions, filling everything. That light is still traveling. Stretched by 13.5 billion years of cosmic expansion into the microwave range, far below the threshold of human vision, it arrives at your location right now from every point in the sky simultaneously. Sensitive instruments can detect it as a faint, uniform warmth. You are bathed, at this moment, in the oldest light the universe has ever released. Stars do not twinkle. If you were floating in space, above the atmosphere, every star in the sky would appear as a perfectly steady, unwavering point of light. The twinkling you see on a clear night is not happening up there. It is happening here, all around you, in the air itself. The atmosphere is never still. Pockets of air at different temperatures and densities are constantly moving, and as starlight passes through them, it is bent slightly, redirected, arriving at your eye from a fraction of a degree in a slightly different direction from one moment to the next. This happens many times per second. The star is steady. The air between you and the star is dancing, and the dance casts its movement onto the light as it passes through, the way a reflection in water moves without the object above it moving at all. The moment light enters your eye, it stops being light in any simple sense and becomes something far stranger. A photon strikes a molecule called retinal, tucked inside a rod or cone cell at the back of your retina. The retinal changes shape. That shape change triggers a cascade of chemical reactions that alter the electrical state of the cell. That electrical change propagates along the optic nerve, arrives at the visual cortex at the back of your brain, and somewhere in that journey, in a process neuroscience has mapped with great care, but not fully explained, it becomes what you experience as seeing. The photon itself is gone. What it leaves behind is a chain of molecular events that your brain translates into color, depth, movement, and meaning. You do not see light. You see what your body decides to make of it. And that decision, made in fractions of a second, remains one of the quieter mysteries at the edge of consciousness. A shadow is not empty. It is not the absence of everything. It is the precise record of a shape, the exact silhouette of whatever stood between a light source and a surface, preserved in the only medium available, which is the absence of photons in a specific region. A shadow is a portrait drawn by subtraction. Ancient sundials read time from shadows, trusting them to be accurate enough for daily life. Architects in ancient Rome designed buildings so that shadows fell on specific points at specific hours. The shadow of the Earth falling on the Moon is what creates a lunar eclipse, and its curved edge was one of the earliest observations used to argue that the Earth is round. A darkness with edges is still a record. Even where light is missing, it leaves the outline of what stopped it, quietly faithful to the shape of the world. A gamma ray and a radio wave are both light. They are both electromagnetic radiation, both traveling at the same speed in a vacuum, both obeying the same physical laws. The difference between them is purely frequency, and through frequency, energy. A gamma ray oscillates at frequencies above 10 billion hertz, carrying enough energy to break molecular bonds and ionize atoms. A radio wave oscillates at frequencies as low as a few thousand hertz, carrying so little energy per photon that it passes through walls and bodies without interaction, wrapping around the curvature of the planet. Between these two extremes lies everything: X-rays, ultraviolet, visible light, infrared, microwaves, and radio, a continuous family of phenomena that human language has divided into separate categories, but the universe regards as a single, unbroken spectrum. The warmth on your face and the radiation from a dying star are cousins, separated only by frequency. When a comet approaches the sun and grows its glowing tail, that tail always points away from the sun, not behind the comet, in the direction of its motion, but directly away from the sun, regardless of which way the comet is traveling. One of the forces responsible for this is radiation pressure, the gentle push of sunlight against the particles of dust and gas streaming from the comet's surface. This force is so small that centuries of astronomers dismissed it as negligible. The first serious calculation of its effect on cometary tails was made in the early 20th century, and even then, the numbers were almost too delicate to believe. Sunlight, the same light warming your face on an afternoon in early spring, is slowly, continuously, and measurably reshaping the tails of comets as they pass through the inner solar system. The sun pushes the universe around with its light, one gentle nudge at a time. In 1905, a young Albert Einstein submitted a paper explaining a puzzling observation that had troubled physicists for years. When light struck certain metals, it knocked electrons free. This was not surprising. What was surprising was that the energy of those electrons depended not on the brightness of the light, but on its frequency. A dim violet light freed electrons. A brilliant red light freed none at all. Einstein explained this by proposing that light was not a continuous wave but a stream of discrete packets, each carrying energy proportional to its frequency. The idea was controversial. It contradicted the prevailing understanding of light as purely wave-like. It earned him the Nobel Prize in 1921, not for relativity, but for this, the photoelectric effect, which quietly underpins every solar panel generating electricity right now, on rooftops all over the world, including perhaps somewhere near where you are resting tonight. There is a geometry at which light, meeting the boundary between two materials, cannot cross. If a beam of light inside a denser medium strikes the boundary with a shallower angle than what physicists call the critical angle, it is reflected completely back into the medium. Not partially, not mostly, but entirely. Not a single photon passes through. This is total internal reflection, and it is a consequence of pure geometry, of the relationship between the angles and the speeds of light in the two materials. It requires no mirror, no coating, no special surface. The boundary itself, shaped correctly, becomes a perfect reflector. Diamonds are cut to exploit this, trapping light inside their facets until it exits in concentrated brilliance. Fiber optic cables use it to carry light across oceans. The universe contains surfaces that reflect perfectly, and they are made of nothing more than the right angle and the right arrangement of materials. The universe has a speed limit. Nothing that carries information, nothing with mass, nothing with any physical effect on the world, can travel faster than light in a vacuum. This is not a technological barrier that a more advanced civilization might one day overcome. It is woven into the structure of space-time itself. As an object with mass accelerates, it requires more and more energy to continue accelerating, and the mathematics shows that reaching the speed of light would require infinite energy. The limit is not enforced by any external rule. It emerges from what space and time actually are, from the geometry of the universe. Light travels at this limit not by straining against it, but because it has no mass, and massless things naturally travel at the maximum speed the universe permits. The speed limit exists not to constrain. It exists because the universe is shaped in a way that makes exceeding it structurally impossible. The most powerful lasers ever built are not designed to cut or communicate or measure. They are designed to compress energy into a space and a moment so small that the conditions briefly rival those at the center of the sun. In facilities like the National Ignition Facility in California, 192 laser beams converge simultaneously on a target smaller than a pea, delivering temperatures and pressures intended to initiate nuclear fusion. The photons doing this work are massless. They weigh nothing. They have no substance in the ordinary sense of the word. And yet, organized and focused, they can briefly create temperatures exceeding 100 million degrees. Light, the thing that arrives gently through a curtained window on a quiet morning, is also the most powerful tool humanity has ever aimed at a controlled target. The difference between the two is not what the light is. It is only how carefully it has been gathered. Long before GPS, long before compasses were understood, Polynesian navigators crossed the Pacific Ocean, using a system of knowledge so refined and so subtle that modern scientists are still working to fully document it. Among the cues they read was starlight, not simply the positions of stars, but their colors, their rising and setting points on the horizon, and the way the quality of light changed with latitude and season. A navigator lying in the hull of a canoe at night could feel the swell of the ocean, watch the stars wheel overhead, and know with confidence where land lay across thousands of kilometers of open water. These were not approximate guesses. These were systematic, inherited, refined readings of the natural world, including its light. The stars were not decoration. They were a map, and those who learned to read it carried their people safely across the largest ocean on Earth. The universe is expanding. Every galaxy beyond our local group is moving away from us, and the farther away it is, the faster it recedes. This expansion stretches the wavelength of light as it travels through space, shifting it toward the red end of the spectrum in a process called cosmological redshift. Light from the most distant objects ever detected has been stretched so dramatically during its journey that it has shifted entirely out of the visible range, arriving not as light the eye can see, but as infrared radiation detectable only by instruments cooled to temperatures near absolute zero. The James Webb Space Telescope was designed specifically to see this shifted light. What it reveals are galaxies forming less than 300 million years after the Big Bang, objects so old and so distant that the light we receive from them was emitted before the Earth existed, before the Sun existed, before the Milky Way had taken its current shape. Some molecules, when struck by light of one frequency, do not simply reflect or absorb it. They hold it for a brief moment and release it at a lower frequency, converting high-energy light into a softer glow. This is fluorescence. Inside your laundry detergent, fluorescent compounds absorb ultraviolet light, invisible to the eye, and re-emit it as visible blue-white light, making washed clothes appear brighter than the light falling on them seems to justify. In the deep ocean, creatures in permanent darkness produce and detect fluorescent signals, invisible to most other animals. A private conversation conducted in wavelengths no predator nearby can see. A single physical phenomenon, the quiet conversion of one frequency of light to another, serves both the most mundane domestic product in your home and the most elaborate signaling system in one of the least explored places on Earth. You cannot visit a rainbow. You cannot walk toward it, because it moves with you, always maintaining its precise, angular relationship between the sun behind you, the raindrops ahead of you, and your eye at the center of the arrangement. A rainbow is not a thing located in the sky. It is a geometric relationship, a set of angles, and it exists only for you, at this moment, from this position. Someone standing beside you sees a slightly different rainbow, centered on their own eye, constructed from different raindrops. The rainbow in a photograph is the rainbow that existed at the position of the camera lens. It is not quite the same as the one you saw. Every rainbow ever witnessed has been a private construction, assembled specifically for the observer standing in that exact place, and it dissolves the moment the light or the position changes. What you saw was real, and it was made entirely for you. There is a galaxy so far from us that its light has spent more than 13 billion years crossing the universe to arrive here. The galaxy that emitted that light may no longer exist in any form we would recognize. Stars that burned inside it have long since exhausted their fuel and collapsed. The structures visible in the light reaching us now are a record of a universe so young it had barely begun to form. We are not seeing that galaxy as it is. We are seeing it as it was, in its earliest youth, while our own galaxy and sun and planet had not yet begun to assemble from the same ancient dust. Every deep-field image of the cosmos is a photograph of the past, layered with different depths of time, nearer objects more recent, farther objects more ancient. The whole image, a quiet archive of moments the universe has already moved through and left behind. Light has a hidden orientation. A beam of ordinary light vibrates in all directions perpendicular to its path. A chaotic shimmer of electromagnetic oscillation spreading outward like the surface of a disturbed pond in 3 dimensions simultaneously. But light can be filtered so that it vibrates in only one plane, aligned, organized, quiet. This is polarization, and it is invisible to the human eye without assistance. Bees and mantis shrimp and certain migratory birds can detect it directly, using polarized skylight as a navigational compass, even on overcast days when the sun itself is hidden. Polarized sunglasses work by blocking light vibrating in the horizontal plane, the orientation produced by reflection from flat surfaces like water and roads. You have worn, perhaps for years, a filter that selects for one invisible property of light, without the filter ever announcing what it was doing. Light contains dimensions of information your unaided senses cannot access. Before mechanical clocks, before pendulums, before any device that measured time through its own motion, there were rooms built to let light do the measuring. In ancient observatories from Egypt to Mesoamerica to India, architects placed apertures, narrow slits, and circular openings in precisely calculated positions so that a beam of sunlight would fall on a marked surface at a specific moment, on a specific day. The winter solstice was announced not by a calendar, but by a shaft of light, crossing a stone floor at dawn and touching a carved mark that had waited in darkness for a full year. These were not decorations or spiritual gestures in isolation. They were functional instruments, using the geometry of the sun's path and the constancy of light's travel to measure time with enough precision to guide planting, ceremony, and governance. Light was the original clock, and architecture was its face. If you send a single photon toward a barrier with two narrow slits and place a detector screen behind it, something happens that resists every intuition the everyday world has given you. The photon produces an interference pattern on the screen, a series of light and dark bands that only makes sense if the photon traveled through both slits simultaneously and interfered with itself. If you add a detector to discover which slit the photon actually passed through, the interference pattern disappears, and the photon behaves like a simple particle. The act of observation changes the outcome. Physicists have confirmed this in hundreds of variations of the experiment, with photons, electrons, and even large molecules. The mathematics of quantum mechanics describes it precisely. What it means, what is actually happening when no one is watching, remains one of the most genuinely and deeply unresolved questions in all of science. Measurement and reality are not, at this scale, independent of each other. In a nuclear reactor submerged in water, there is sometimes a blue glow that seems to emerge from the water itself, cool and constant, surrounding the fuel rods like a faint, luminous breath. This is Cherenkov radiation, and it occurs because certain particles produced by the reactor travel through water faster than light can travel through water. Light in water moves at roughly 75% of its vacuum speed, and particles can exceed this reduced limit without violating any physical law, since the universal speed limit applies only in vacuum. When a charged particle overtakes light in a medium, it produces a photonic shock wave, a cone of blue light analogous to the sonic boom of an aircraft exceeding the speed of sound. The blue glow is the universe's way of marking the passage of something moving faster than light can follow through that particular medium. A quiet announcement written in color. The human eye, under ideal conditions, in complete darkness after full adaptation, can detect as few as 5 to 7 photons arriving at the retina within a brief window of time. This is not an average. It is a genuine physical threshold, close to the absolute minimum permitted by quantum mechanics. Below this, the statistical noise of random thermal fluctuations in the retinal cells overwhelms the signal. At this threshold, you are not seeing in any robust sense. You are at the edge of the possible, registering the faintest physical event your biology can distinguish from silence. Evolution shaped this sensitivity across millions of years of navigating darkness, and it placed you precisely at the boundary where quantum effects and biological machinery meet. The eye you are resting right now, closed perhaps, or open in a lit room, is an instrument of extraordinary delicacy, calibrated to the edge of what physics permits. In medieval Scandinavia, navigators sailing under overcast skies used a mineral called Iceland spar to find the position of the sun. Iceland spar is a transparent form of calcite with strong birefringent properties, meaning it splits light into two polarized beams. By rotating the crystal while looking through it at different parts of the sky, a navigator could identify the point where the brightness of the two beams equalized, which corresponds to the direction of the sun, even when the sun itself is hidden behind cloud. Recent analysis of a crystal found on a 16th century shipwreck confirmed it matches the optical properties needed for this purpose. For centuries, sailors crossed open ocean using a transparent stone and the hidden polarization pattern of skylight, a technology so subtle it left almost no written record, known mainly through a single mention in a medieval saga and the quiet evidence of the crystal itself. Light carries more than energy and color. It carries angular momentum, a property called spin, and this spin can be transferred to physical objects. A circularly polarized beam of light, one whose electric field rotates as it travels, can exert a torque on small particles that absorb it, causing them to rotate. This is not a theoretical curiosity. Physicists use precisely engineered laser beams to rotate individual microscopic particles, including living biological cells and organelles inside cells, without touching them, without any mechanical contact whatsoever. The handle is light. The rotation is real and measurable. Researchers have used this technique to study the mechanical properties of cell membranes and the forces generated inside living tissue. Light, which you experience as something that arrives and illuminates, is also something that can reach into a living cell and turn it, gently and precisely, like a hand that leaves no mark. In ordinary light, the waves are chaotic. Photons arrive at different times, vibrating in different directions, carrying slightly different frequencies, a crowd moving through a space with no coordination. In a laser, something different happens. Through a process of stimulated emission, the photons are brought into coherence, all vibrating at the same frequency, all in phase with each other, all traveling in the same direction. This coherence is extraordinarily rare in nature. Almost no natural light source produces it. It requires an engineered environment, a gain medium, mirrors to reflect photons back and forth, and carefully controlled conditions. When it is achieved, the result is a beam of light so organized it can remain tightly focused across vast distances, a quality that makes lasers useful for surgery, for measurement, for communication, and for reaching the moon. Coherence, in light as perhaps in other things, produces a precision that chaos, however energetic, cannot achieve. The light of the moon is not the moon's own. The moon produces no light of its own, no internal fire, no bioluminescence, no chemical glow. What you see on a clear night, that soft silver presence that casts faint shadows on quiet roads, is sunlight. It left the sun, traveled 150 million kilometers to reach the lunar surface, and was reflected from ancient gray dust at an efficiency of only about 12%, the moon being one of the least reflective bodies in the solar system. Then it traveled another 384,000 kilometers to reach your eye. The moonlight arriving on your face right now has been traveling for approximately 1.5 seconds since it left the lunar surface, and for about 8 minutes before that since it left the sun. What feels intimate and close is a messenger from 150 million kilometers away, softened by distance and reflection into something almost tender. Light can be used to stop atoms, not to push them, as radiation pressure does, but to bring their thermal motion, their restless microscopic vibration, almost to a halt. This technique, called laser cooling, works by directing laser beams tuned to a precise frequency at a cloud of atoms from multiple directions simultaneously. Atoms moving toward a beam encounter its photons at a slightly higher frequency due to the Doppler effect, making the interaction more likely. Each absorbed photon transfers a tiny impulse opposing the atom's motion. Over millions of such interactions per second, the atoms slow. Their temperature, which is simply a measure of their average motion, drops toward absolute zero. Using this method, physicists have cooled clouds of atoms to temperatures measured in billionths of a degree above absolute zero, the coldest temperatures known to exist anywhere in the universe, colder than the void between galaxies, achieved with precisely aimed beams of light. Near the poles of the Earth, on clear dark nights, the sky sometimes fills with light that moves. Curtains of green and violet and white ripple across the upper atmosphere in slow, continuous motion, brightening and fading without sound, without warning, without the sense that anything has begun or ended. This is the aurora, produced when charged particles streaming from the sun follow Earth's magnetic field lines into the upper atmosphere and collide with oxygen and nitrogen atoms, exciting them into emitting light. The specific colors depend on which gas is involved and at what altitude. Green comes from oxygen at lower altitudes, red from oxygen higher up, blue and violet from nitrogen. Ancient Norse peoples called the aurora the Bifrost Bridge. Indigenous peoples of North America heard them as voices. For as long as humans have looked upward at night, this moving light has arrived without explanation and departed without resolution, as beautiful now as it was before anyone knew what caused it. Every plant you have ever seen, every tree, every blade of grass, every floating algae in the ocean, sustains itself by capturing light. The process begins with a single photon striking a chlorophyll molecule inside a chloroplast, exciting an electron to a higher energy state. What happens next involves quantum mechanics in a way that still surprises researchers. The energy does not wander randomly through the photosynthetic complex searching for the reaction center. It explores multiple pathways simultaneously through a process related to quantum superposition and finds the most efficient route with a speed and reliability that no classical process could match. The efficiency of this quantum step approaches 95% under optimal conditions, a figure that no human-engineered solar technology has yet matched. Every leaf is running a quantum computation, quietly, continuously, in the sunlight of an ordinary afternoon, and the full details of how it achieves this remain an open and active area of research. Inside the gain medium of a laser, something happens at the level of individual atoms that makes the whole device possible. An atom, already in an excited energy state, is struck by a photon whose frequency matches exactly the energy difference between the atom's excited state and its ground state. Instead of absorbing this photon, the atom releases a second photon, identical to the first in frequency, phase, and direction. This is stimulated emission, predicted by Einstein in 1917, more than 3 decades before the first laser was built. One photon becomes 2. Those 2 stimulate 2 more. The cascade grows. Mirrors at each end of the laser bounce the photons back and forth through the gain medium, amplifying the cascade until a portion of the beam is released through a partially reflective mirror as the laser output. What seems like a beam of concentrated light is actually a chain reaction of atoms releasing copies of the same photon over and over in perfect agreement. Red light and blue light travel at the same speed in a vacuum, but they do not move through the world with equal ease. Red light, with its longer wavelength, passes through fog, dust, smoke, and haze more readily than blue light, whose shorter wavelength scatters more easily against small particles suspended in the air. This is why traffic signals use red for stop, why maritime warning lights are red, why the setting sun turns red and orange as its light travels a longer path through the atmosphere and the blue wavelengths scatter away before reaching you. It is also why the landscapes of early mornings and late evenings carry a warmth and depth that midday light, arriving more directly, does not. The emotional register of red light, its association with warmth, with slowness, with the hour when the day lets go, is written into the physics of how that wavelength moves through the world. A solar sail is not a metaphor. It is a real spacecraft propulsion concept, and several have been tested in orbit. The principle is simple. Light carries momentum. When photons strike a reflective surface, they transfer that momentum, producing a small but continuous thrust. In the vacuum of space, where there is no friction and no competing force, this thrust accumulates. Over weeks and months and years, a large enough sail, made of thin enough material, can accelerate a small spacecraft to significant velocities without any fuel, using only the continuous pressure of sunlight. The Planetary Society's Light Sail 2 demonstrated controlled solar sailing in Earth orbit in 2019. Future missions may use this principle to reach nearby star systems over timescales of decades. The Sun has been pushing things with its light for 4.5 billion years. We are only now learning to let it push us somewhere deliberately. Certain minerals, exposed to sunlight or other radiation over geological timescales, store that energy inside their atomic structure in the form of displaced electrons trapped at defects in the crystal lattice. When these minerals are gently heated in a laboratory, the electrons return to their ground states and release the stored energy as a faint glow of light. This phenomenon, thermoluminescence, is used by archaeologists and geologists to date ancient materials, measuring how long ago a pottery shard was fired or how long ago a sediment layer was last exposed to sunlight. The mineral is, in this sense, a clock, ticking in the dark, waiting for warmth to make it speak. Ancient ceramics hold within them the memory of a fire that burned thousands of years ago, and heating them gently in a laboratory causes them to re-emit, very faintly, a light that is in some sense a record of that original burning. The observable universe is a sphere with a radius of approximately 46 billion light-years. This sphere is not the full extent of the universe, only the portion from which light has had time to reach us since the Big Bang. Beyond that horizon, space continues, perhaps infinitely, filled with matter and energy and structure that is in principle identical to what we can see. But because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, everything beyond that horizon is permanently invisible to us. We cannot send a signal there. We cannot receive one from there. The boundary of everything we will ever know is drawn entirely by the speed of light and the age of the universe. We live inside a sphere of knowability, and light is what defines its walls. Inside a glass prism, white light separates into its component colors because different wavelengths refract or bend by slightly different amounts as they cross the boundary between air and glass. Violet light bends more than red. The small angular difference accumulates across the width of the prism until the colors emerge on the far side as a continuous fan, each wavelength occupying its own position in space. Isaac Newton performed this experiment in 1666 and went further, recombining the separated colors with a second prism to restore white light, demonstrating that the prism was not coloring the light, but revealing what was already present within it. What appears as unity is a plurality traveling together. What appears as simplicity is a complex agreement between wavelengths that remain, at all times, individually distinct, choosing to arrive together at your eye as the experience of whiteness, and separable, always, into their separate voices. The deep ocean is the largest living space on Earth, and much of it exists in complete darkness where sunlight cannot penetrate. In this darkness, life developed light of its own. Bioluminescence, the production of cold light through chemical reactions, has evolved independently in at least 40 separate lineages of marine organisms, including fish, jellyfish, squid, bacteria, and plankton. The same basic chemistry, involving a molecule called luciferin and an enzyme called luciferase, was arrived at independently across species separated by hundreds of millions of years of evolution. The ocean kept finding the same answer to the same problem. Light, produced without heat, for communication, for camouflage, for attracting prey, or for reasons still unknown, arose again and again in the darkness as though the absence of light creates its own quiet pressure toward illumination. The deep ocean is full of creatures that decided, independently, to become their own light source. The James Webb Space Telescope orbits the Sun at a point approximately 1.5 million kilometers from Earth, kept cold by a sun shield the size of a tennis court. Its primary mirror, 6.5 meters across, collects infrared light that has been traveling for more than 13 billion years. The sensitivity required for this is almost beyond description. Engineers have compared it to detecting the heat of a single honeybee at the distance of the Moon. To achieve this, The telescope must be kept at a temperature of -233 degrees Celsius, just 40 degrees above absolute zero. Every image it returns is a record of the early universe, structures that formed when the cosmos was less than 5% of its current age. We built a machine, floated it in space, cooled it to near absolute zero, and pointed it at the past. And the past has been answering. Every flame has a signature. When the molecules inside a burning substance are excited by heat, their electrons jump to higher energy states and then fall back, releasing photons of very specific wavelengths as they do. Those wavelengths are not random. They are determined by the precise electronic structure of each element, as fixed and individual as a fingerprint. Sodium burns yellow, copper burns green, lithium burns red. A spectroscope, splitting that light into its component wavelengths, can read the chemical composition of a flame from across a room or across a galaxy. This is how astronomers know what distant stars are made of, by analyzing the specific wavelengths present or absent in their light. A candle flame on a table is broadcasting its chemistry and light at this moment, a message precise enough to be decoded, waiting quietly for an instrument sensitive enough to read it. The first permanent photograph ever made required approximately 8 hours of exposure to light. In 1826, Joseph Nicephore Niepce coated a pewter plate with bitumen of Judea, a naturally occurring asphalt that hardens when exposed to light, and placed it in a camera obscura aimed at the view from his upstairs window. After a full day of exposure, the light had hardened the bitumen where it struck most intensely, and washing away the unhardened portions, revealed a faint, grey image of rooftops and sky. Light had written its first self-portrait onto a physical surface. What followed, in the nearly 2 centuries since, is a continuous elaboration of that same principle. Light striking a sensitive surface and leaving a record of what it touched. Every photograph ever taken is a descendant of that first 8-hour conversation between sunlight and a coated plate on a windowsill in Burgundy. Inside the molecular machinery of photosynthesis, there is a step that classical physics cannot account for. After a photon is absorbed by a chlorophyll molecule and its energy begins moving toward the reaction center where it will drive chemistry, the energy does not hop randomly from molecule to molecule the way a classical particle would. Instead, it appears to exist in a superposition across multiple pathways simultaneously, sampling all available routes at once and collapsing toward the most efficient one. This quantum coherence, observed in photosynthetic complexes at room temperature, surprised researchers when it was first detected in 2007, because quantum effects of this kind were expected to be destroyed almost instantly by the warm, wet, noisy environment of a living cell. Life, it appears, has found a way to harness quantum mechanics, not in a cold laboratory, but in the ordinary warmth of a sunlit leaf. How it protects this coherence from the thermal noise surrounding it remains an open question. A neutron star is the collapsed remnant of a massive star, compressed to a sphere roughly 20 kilometers across, while retaining more mass than the Sun. Its gravitational field is so intense that light traveling across its surface is bent into a curved path, following the curvature of space-time, rather than traveling in a straight line. The degree of bending is so extreme that from a sufficient distance, you can observe not just the hemisphere of the star facing you, but a portion of the hemisphere facing away, because light from the far side curves around the star and arrives at your instruments. Astronomers use this property to study the geometry of neutron star surfaces, measuring how much of the star is visible from various angles to infer the relationship between the star's mass and its radius. A dead star bends light around itself so severely that it shows you its own back. The universe contains more matter than we can see. Across galaxy clusters, and along the vast filaments of cosmic structure, there exists a form of matter that emits no light, reflects no light, and absorbs no light, interacting with the electromagnetic spectrum in no detectable way. We call it dark matter, and we know it exists primarily because of how it bends light. As photons from distant background galaxies pass through or near a cluster of dark matter, their paths curve in response to its gravitational field, distorting the shapes of the galaxies behind it in a pattern called gravitational lensing. By mapping these distortions across the sky, astronomers have assembled maps of the dark matter distribution in the universe, tracing the invisible by reading the bending of the visible. Light, which cannot touch dark matter, has nevertheless become our primary tool for understanding where it is. Fireflies carry within them a chemistry that produces light without heat, a cold illumination generated by the reaction of a molecule called luciferin with oxygen in the presence of an enzyme. This chemistry evolved separately from the bioluminescence found in marine organisms, arriving at a parallel solution through an entirely independent evolutionary path. The light produced is extraordinarily efficient, converting nearly all the chemical energy into photons, with almost no waste heat, an efficiency that far exceeds any incandescent bulb and rivals modern LEDs. Researchers studying firefly luciferase have used it as a biological marker in laboratory research, attaching the light-producing gene to other organisms to make cellular processes visible. A firefly rising in a field on a summer evening is demonstrating, without any awareness of doing so, a chemistry so efficient and so elegant that human engineers are still working to understand and replicate it fully. When a source of light moves toward you, its waves are compressed, arriving more frequently, shifting the light toward shorter wavelengths, toward blue. When it moves away, the waves are stretched, arriving less frequently, shifting the light toward longer wavelengths, toward red. This is the Doppler effect applied to light, and it is how Edwin Hubble, in 1929, demonstrated that galaxies are moving away from us, and that the farther a galaxy is, the faster it recedes. From this, the expanding universe was confirmed. From the expanding universe, the Big Bang was inferred. From the Big Bang came our current understanding of cosmic history, the age of the universe, the formation of elements, the origin of structure. All of this, the entire modern cosmological story of where everything came from, began with the observation that the light from distant galaxies was shifted slightly toward red, a detail so subtle that it required extraordinarily careful measurement to detect. Between two uncharged parallel metal plates held very close together, in what appears to be a perfect vacuum, there is a force. The plates attract each other, measurably, consistently, with a strength that increases as they are brought closer together. This is the Casimir effect, and it arises because even in the apparent emptiness between the plates, the quantum vacuum is not empty. It seethes with fleeting fluctuations of the electromagnetic field, virtual photons flickering in and out of existence too briefly to be individually detected. The space outside the plates accommodates more of these fluctuations than the space between them, creating a slight pressure imbalance that pushes the plates together. Empty space, it turns out, is not a passive absence. It is an active medium, and the light it contains, however briefly, has measurable physical consequences. Darkness, at the quantum level, is full. The color you call red is a frequency of electromagnetic radiation between approximately 620 and 750 nanometers. Your eye detects it. Your brain constructs an experience from it. But whether the experience you call red, the felt inner quality of it, the specific character of redness as you know it privately, matches what anyone else experiences when they look at the same object, is a question that science has not answered and may not be able to answer with current tools. There is no instrument that reads subjective experience. There is no way to compare the inner quality of one person's red with another's. Philosophers call this the problem of qualia. Neuroscientists study the neural correlates of color perception without yet reaching the felt experience itself. The wavelength is measurable to extraordinary precision. What your nervous system does with it, in the private space where seeing becomes experience, remains entirely your own. The most precise clocks ever built use the behavior of light to measure time. Optical atomic clocks track the frequency of light emitted by atoms of strontium or ytterbium, as their electrons oscillate between energy levels, a frequency so stable and so high that the clock would neither gain nor lose a single second over 300 million years. These clocks are so precise that they can detect the gravitational time dilation predicted by general relativity between two clocks separated vertically by just a few centimeters. The clock higher up, in a slightly weaker gravitational field, runs measurably faster. This is not a flaw in the clocks. It is a confirmation that time itself passes at different rates depending on the strength of gravity. A difference so small that only a clock calibrated by the frequency of light could detect it. Time is not uniform. Light is what reveals this, at the limit of what any instrument has ever measured. At Karnak in Egypt, at Newgrange in Ireland, at the Majorville Medicine Wheel in Alberta, and at dozens of other ancient sites across the world, architects built chambers and corridors aligned with the precision of astronomical instruments, so that sunlight would enter only on specific days of the year. At Newgrange, a passage tomb constructed more than 5,000 years ago, a small aperture above the entrance door allows a beam of winter solstice sunrise to travel the full length of the 19-meter corridor and illuminate the inner chamber for approximately 17 minutes. This alignment is accurate to within a degree. The builders had no written mathematics, no telescopes, no mechanical instruments. They had time, careful observation, and an understanding of how light moves through a landscape across seasons. They built their knowledge into stone so that the light itself would confirm it once a year for millennia. A photon of visible light carries so little energy that it would require approximately 100 trillion of them arriving together to equal the kinetic energy of a single falling raindrop. 100 trillion. The number is almost impossible to hold in the mind, and yet this is the scale at which light operates individually, at the edge of the measurable, each photon a vanishingly small carrier of energy. And yet, in aggregate, these same photons drive every process of life on Earth. They split water molecules inside chloroplasts. They power the currents of the ocean through differential heating. They drive the water cycle that fills every river and cloud. They warm the ground beneath your feet and the air in your lungs. The cumulative effect of particles, individually too small to feel, is the entire living system of a planet. Scale changes everything, and light demonstrates this more quietly and completely than almost anything else. In a glass of water, under the right conditions, a sound wave can create a tiny bubble that collapses so rapidly and so violently that for a fraction of a second, the temperature inside it reaches tens of thousands of degrees, briefly rivaling the surface of the sun. In that fraction of a second, the collapsing bubble emits a flash of light. This phenomenon is called sonoluminescence, and it has been observed reliably in laboratories since the 1930s. What is less certain is the precise mechanism by which the energy of a collapsing sound bubble is converted into light. Several competing explanations exist, involving plasma formation, quantum radiation effects, and other processes. None has been fully confirmed. A glass of water, subjected to the right frequency of sound, will produce light by a mechanism that scientists have been debating for nearly a century. The kitchen contains mysteries that physics has not finished with yet. The speed of light is not simply a fast number. It is the conversion factor between space and time, the rate at which these two things exchange with each other in the geometry of the universe. Einstein's equation, expressing the equivalence of mass and energy, contains the speed of light squared, revealing that mass is a form of frozen energy, and that the two are related by a constant written into the structure of space-time. The speed of light also appears in Maxwell's equations of electromagnetism, in the equations of special relativity, in the relationship between electric and magnetic fields, in the quantum mechanical description of the hydrogen atom, and in dozens of other places across physics, always as a bridge between quantities that seem, on the surface, to be different kinds of things. It is not merely how fast light travels. It is a number the universe uses to relate space to time and matter to energy, woven through the structure of everything. A galaxy cluster sitting between us and a more distant galaxy acts as a gravitational lens, bending and focusing the light from the background galaxy, the way a glass lens bends light passing through it. But unlike a glass lens, the gravitational lens can amplify the light of the background object by a factor of hundreds or even thousands, making objects visible that would otherwise be far too faint to detect with any instrument yet built. In some cases, the same background galaxy appears multiple times in the same image, its light having taken several different curved paths around the foreground cluster and arrived at the telescope from multiple directions simultaneously. The lensing cluster itself may contain no visible matter at all, its mass composed entirely of dark matter detectable only through the bending it causes in the light passing by. We see the invisible by the shape it bends into the visible. In the early 19th century, a Bavarian glassmaker named Joseph von Fraunhofer was working to improve the quality of optical glass by studying the spectrum of sunlight with unusual precision. He noticed dark lines crossing the spectrum at specific fixed positions. Hundreds of them, always in the same places, always the same widths. He mapped them carefully, without knowing what they meant. Decades later, other scientists would realize that these dark lines, now called Fraunhofer lines, are produced by specific elements in the sun's outer atmosphere, absorbing specific wavelengths of light as it passes through. Each element removes its own precise wavelengths, leaving a gap in the spectrum. By reading these gaps, astronomers can determine the chemical composition of a star without visiting it, without sampling it, using only the light it sends. Fraunhofer found the gaps. He did not yet know he was reading the sun's own list of ingredients, written in the language of absence. When light from a distant exoplanet passes through or reflects from that planet's atmosphere before reaching a telescope, it carries within it the chemical fingerprints of whatever gases are present. Certain molecules absorb certain wavelengths, leaving characteristic gaps in the spectrum, the same principle that allows astronomers to read the composition of stellar atmospheres. By analyzing these absorption signatures, researchers can detect the presence of water vapor, carbon dioxide, methane, or oxygen in the atmosphere of a planet orbiting another star. The James Webb Space Telescope has already detected carbon dioxide in the atmosphere of an exoplanet hundreds of light years away. Astronomers are now designing future missions capable of detecting the specific combination of gases that, on Earth, is produced and maintained by biology. We may, within the coming decades, find the signature of life written in the spectrum of a distant world's light, if it is there to be found. There is a medical imaging technology that uses light in a way that feels closer to listening than looking. Optical coherence tomography directs pulses of near-infrared light into living tissue and measures the time it takes for those pulses to reflect back from structures at different depths. By comparing these reflected signals, the instrument builds a three-dimensional map of the internal structure of the tissue, layer by layer, with a resolution of just a few micrometers. In ophthalmology, it allows doctors to examine the individual cellular layers of the retina, the thin, light-sensitive membrane at the back of the eye, without any physical contact. A beam of light enters the eye, reflects from the retina, returns with information about its own structure. Light is being used to look at the very tissue that normally does the looking, examining the instrument of sight from the inside, with the same phenomenon that instrument was built to receive. The event horizon of a black hole is not a surface you could touch or see. It has no wall, no membrane, no visible boundary. It is defined entirely by geometry. It is the location in space beyond which the curvature of space-time is so severe that every possible path through space, including paths taken by light, leads inward. If you were crossing the event horizon, you would notice nothing at the moment of crossing. No alarm would sound, no surface would stop you. Only later, as the geometry continued to tighten around you, would the consequences become apparent. The boundary is invisible, is defined by mathematics, and marks the point where the direction we call away simply ceases to be geometrically available. It is perhaps the most absolute boundary in the universe, not enforced by any force, not built of any material, but simply the place where the universe runs out of directions that lead out. Seeing a single photon does not feel like anything you would recognize as vision. Under ideal laboratory conditions, with fully dark-adapted eyes, a human subject can report detecting a flash when as few as 5 to 7 photons arrive at the retina within a brief window. But this perception is uncertain, probabilistic, hovering at the edge of reportable experience. The photons that trigger this threshold response must survive passage through the cornea, the lens, and the vitreous humor, and only a fraction of those that enter the eye will strike a rod cell in a position sensitive enough to contribute to the signal. Once they do, the rod cell amplifies the signal through a cascade involving hundreds of protein molecules, each step multiplying the initial quantum event until it becomes a nerve impulse, then a pattern across the optic nerve, then something your brain interprets as a faint, uncertain presence in the dark. The universe allows you to notice its smallest particles of light. It simply asks that you be very quiet and very still to do so. Light can be made to stop, not slowed, as it is in glass or water, but held, suspended inside a crystal in a state that preserves its quantum information without allowing it to travel. In certain experiments using rare earth-doped crystals, a pulse of light is directed into the crystal and absorbed by a carefully prepared ensemble of atoms. The light's quantum state is transferred into the collective spin state of those atoms and held there, motionless, for fractions of a second. Then, on command, a second laser pulse causes the atoms to release the stored state as a new pulse of light, emerging with its original properties intact. The light was not destroyed and recreated. It was paused, like a breath held between words, and then released. Scientists are exploring this phenomenon as a foundation for quantum memory, devices that could store light the way ordinary memory stores information, and the questions it raises about what light is when it is not moving remain genuinely open. The word photon was not coined until 1926 by the chemist Gilbert N. Lewis. Before that, the particle of light had no agreed name. Einstein described it in 1905 as a light quantum, a discrete packet of electromagnetic energy, and for 2 decades, this particle that underpins all of modern optics, all of chemistry, all of biology that depends on light, existed in scientific literature without a settled name. Humanity had already split the atom, already built the first radio transmitters, already begun the age of electrical technology, all while still arguing about what to call the fundamental unit of light. The photon is older than its name. It arrived in the universe's first moments and traveled for billions of years before a human mind settled on a word for it. The universe rarely waits for us to finish naming things before it continues with what it was doing. Quantum electrodynamics, the theory that describes how light and matter interact at the quantum level, is the most precisely tested theory in the history of science. Its predictions have been confirmed experimentally to better than 1 part in a billion, a level of accuracy that has no rival in any other domain of human knowledge. And yet, quantum electrodynamics cannot be made to agree with general relativity, the equally successful theory that describes gravity and the large-scale structure of space-time. These two theories, each extraordinarily precise within its own domain, produce mathematical contradictions when applied simultaneously to conditions where both gravity and quantum effects are important, such as the interior of black holes or the first moments after the Big Bang. At the place where light, gravity, and quantum behavior all meet, the two most successful scientific theories ever constructed fall quietly and irreconcilably silent. The universe keeps this particular secret with remarkable consistency. There are materials in which color has no pigment, no dye, no absorbing molecule. No chemical process is responsible for the color you see. Instead, the material is structured at a scale comparable to the wavelength of visible light, and this geometry determines which wavelengths reflect constructively and which cancel each other out through interference. The result is a color that changes with viewing angle, that can be extraordinarily vivid, and that arises entirely from structure. These are called photonic crystals, and they appear in nature in the wings of morpho butterflies, in the feathers of certain birds, and in the shells of some beetles. The iridescent blue of a morpho butterfly wing contains no blue pigment whatsoever. The color is a consequence of geometry, of light interfering with itself across a surface engineered by evolution over millions of years. Some of the most vivid colors in the natural world are, in a precise sense, made of nothing but light and shape. A beam of light exerts pressure. This is established and measurable physics. Applied continuously to a large reflective object in space, this pressure accumulates over time into a meaningful force. Researchers have proposed that a high-powered laser aimed at a small asteroid over years or decades could nudge it onto a different trajectory, diverting it from a collision course with Earth without explosions, without physical contact, using only the continuous, gentle push of photons. This concept, called laser deflection, is one of several planetary defense strategies currently under serious study by space agencies. The force per photon is almost inconceivably small. The number of photons a powerful laser delivers per second is almost inconceivably large. Over the timescales available when a threat is detected early enough, the two balance into something that could, in principle, move a mountain. Light, applied with patience, is capable of protecting a planet. More than 2,000 years ago, a mechanism was built by hand from bronze, small enough to hold, containing at least 30 gears of extraordinary precision, designed to track the cycles of the sun and moon and predict astronomical events, including solar and lunar eclipses. The Antikythera mechanism, recovered from a Greek shipwreck in 1901 and studied intensively ever since, could predict the position of the sun and moon in the sky on any given date, centuries into the future. It was, in essence, a mechanical model of how light from the sun would behave, where it would fall, when it would be blocked, how shadows would cross the face of the moon. The people who built it had no knowledge of photons or electromagnetic radiation. They understood the patterns of light in the sky, with enough precision to encode those patterns in gears. The behavior of light was understood long before light itself was. Every element in the periodic table has its own spectral fingerprint. When an element's atoms are energized, electrons jump to higher energy levels and then fall back, releasing photons of very specific wavelengths as they do. These wavelengths are not approximate, they are fixed by quantum mechanics to values so precise that they can be calculated from first principles and measured in a laboratory to many decimal places. No two elements share the same complete set of spectral lines. This means that a spectroscope, separating light into its component wavelengths, can identify the elements present in any light-emitting source, regardless of distance. Astronomers have used this to determine the chemical composition of stars, nebulae, and galaxies billions of light-years away, identifying hydrogen, helium, carbon, iron, and dozens of other elements in the spectra of objects no human instrument has approached or ever will. The universe labels its contents in light, and we have learned, slowly and carefully, to read the labels. The speed of light in a vacuum is exactly 299,792,458 meters per second, not approximately. Exactly. This precision is not the result of an extraordinarily careful measurement. It is the result of a decision. In 1983, the international scientific community redefined the meter itself as the distance light travels in a vacuum in exactly 1,299,792,458th of a second. By fixing the speed of light as an exact number, the meter became a derived quantity, defined by the behavior of light rather than by any physical artifact. The speed of light, once a measured value with experimental uncertainty, became a definition, a number that anchors the entire international system of length measurement. The fastest thing in the universe now serves as the foundation for how humanity measures all distances, from the width of an atom to the distance between cities. Light defines the ruler. On a hot road or a desert plain, you sometimes see what appears to be water shimmering on the surface ahead, a reflection of the sky that vanishes as you approach. This is a mirage, and it is not an illusion of the mind. It is a real optical phenomenon in which light is bent by layers of air at different temperatures. Near the ground, on a hot day, the air is significantly warmer than the air above, and warmer air is less dense. Light traveling through this temperature gradient is continuously refracted, bent gradually upward from the ground, until it curves back toward your eye from a direction that appears to come from the ground surface. What you are seeing is a real image of the sky, redirected to your eye by the temperature structure of the air. The physics is precise and reliable. The water is real light from a real sky. It is simply the sky arriving from an unexpected direction. Ultraviolet light occupies a narrow band of the electromagnetic spectrum just beyond the visible, with wavelengths shorter than violet light and higher energy per photon. At these energies, photons carry enough punch to break the chemical bonds within DNA, causing mutations in the genetic code of any cell they reach. Over evolutionary time, this mutagenic pressure has been one of the drivers of genetic diversity, and therefore of the variety of life on Earth. At the same time, ultraviolet light striking the skin triggers the synthesis of vitamin D, an essential molecule involved in calcium absorption, immune function, and bone development. The same wavelength of light that can damage the genetic material inside a cell is also required for the cellular processes that keep the skeleton strong. The universe does not arrange its phenomena with human convenience in mind. The same light that can harm is also the light that helps, and the difference is almost entirely a matter of dose. The oldest art ever discovered was made by firelight. Paintings on cave walls in Chauvet, France, dating to approximately 36,000 years ago, depict horses, lions, rhinoceroses, and bears with a sophistication that still surprises researchers who study them. These images were painted in chambers where no natural light reaches, lit only by torches and small lamps burning animal fat. The artists worked in flickering, moving light, and some researchers believe the paintings were designed for this. that the animals were intended to appear to move and breathe as the flame moved, that the art was inseparable from the living quality of its illumination. The first images humanity ever made were not meant to be seen in still, even light. They were meant to be seen in fire. Light was not the medium the first artists worked in. It was the condition they worked for, the environment their art required to become fully itself. A hydrogen atom in a laboratory on Earth, when energized, emits light at a precise set of wavelengths. A hydrogen atom in a galaxy 10 billion light-years away, when energized, emits light at exactly the same set of wavelengths, adjusted only for the redshift of cosmic expansion. The underlying quantum mechanical constants, the mass of the electron, the charge of the proton, the value of Planck's constant, are identical across the entire observable universe, as far as any measurement has ever been able to determine. The laws governing the behavior of light do not vary with location or with time. This is not something that follows logically from any deeper principle we currently possess. It is an observed fact, confirmed across the full extent of our observable universe, that the rules are the same everywhere light has reached. The universe is, as far as light can show us, governed by a single and consistent set of agreements. Inside a solar cell, something happens that requires no moving parts, no heat, no combustion. A photon of sufficient energy strikes the semiconductor material and transfers its energy to an electron, freeing it from its atomic bond and allowing it to flow through the material as electrical current. This is the photovoltaic effect, discovered by Edmond Becquerel in 1839, and it is happening right now in every solar panel, on every rooftop in sunlight anywhere on Earth, in the solar arrays of the International Space Station, in the instruments of the Voyager probes moving through interstellar space, in the surface of the Mars rovers. Sunlight arrives, strikes a surface, and leaves behind a current of electrons moving in one direction, a flow of energy that can charge a battery, power a light, or keep a spacecraft alive across decades of darkness between planets. No machine with moving parts can do what a flat sheet of treated silicon does in silence, in sunlight, all day. If stars were spread evenly and infinitely through an eternal universe, the night sky should not be dark. Every line of sight would eventually terminate at the surface of a star, and the sky would glow uniformly bright in every direction, day and night indistinguishable. The fact that the night sky is dark is not simply because stars are far away. It is because the universe has a finite age. Light from the most distant stars has not yet had time to reach us. The universe is not old enough for every line of sight to have filled with starlight. The darkness of the night sky is therefore not an absence. It is a record of the universe's youth, of how recently it began, of how far light has managed to travel in the time available. You look up at night and see darkness, and what you are actually seeing is the age of everything, written in the places where light has not yet arrived. Optical tweezers are exactly what the name suggests, except the tweezer is made entirely of light. A tightly focused laser beam, converging to a point smaller than a wavelength of light, creates a gradient of electromagnetic intensity that draws small dielectric objects toward the focal point and holds them there. The force is extraordinarily gentle, measured in piconewtons, fractions of a trillionth of a newton, and yet it is sufficient to hold and manipulate single biological cells, individual bacteria, strands of DNA, and even single atoms. Researchers have used optical tweezers to measure the force a single motor protein exerts as it walks along a cellular track, to study how DNA unwinds under tension, and to probe the mechanical properties of living cells without any physical contact. Arthur Ashkin received the Nobel Prize in Physics in 2018 for this work. The most delicate manipulation ever performed in a laboratory is done not with any instrument that touches its subject, but with a focused beam of light. For nearly all of recorded human history, Light was believed to travel instantaneously. Aristotle argued that sight was immediate, that light, if it traveled at all, did so without any measurable delay. Descartes agreed. Galileo attempted to measure the speed of light using lanterns on hilltops, and concluded only that it was very fast, too fast for his method to resolve. The assumption of infinite speed was so intuitive, so consistent with everyday experience, that it persisted until Ole Rømer's observation of Jupiter's moons in 1676 provided the first credible evidence of a finite speed. For most of the time, humans have been asking questions about the natural world. Light was believed to arrive everywhere at once, to touch all things simultaneously, to exist outside the ordinary constraints of travel and time. The discovery that light is not instantaneous, that it journeys, that it can be measured, is only about 3.5 centuries old. The first image ever captured of a black hole was released in April 2019, assembled from data collected by 8 radio telescopes positioned across 4 continents, operating simultaneously as a single virtual telescope the size of the Earth. The image showed a glowing orange ring surrounding a dark central region, the shadow of the black hole in Messier 87, a galaxy 55 million light-years away. The ring is not a simple circle of nearby gas. It is light from the accretion disk, a swirling cloud of superheated material, some of which is behind the black hole and would normally be invisible. The extreme curvature of space-time around the black hole bends that light around the object and redirects it toward the observer, so that the back of the accretion disk is visible wrapped around the front. The first portrait of a black hole is also a demonstration of gravity, doing to light what no lens ever built could do. In quantum optics, there is a phenomenon in which 2 photons, arriving at the same location at the same moment, can combine their energies as though they were a single photon of twice the frequency. This is 2-photon absorption, and it requires an intensity of light so high that 2 photons must arrive within the same infinitesimally brief quantum window to interact simultaneously with a single molecule. Because this interaction only occurs at the precise focal point of a tightly focused laser beam, where the intensity is highest, it allows researchers to excite fluorescent molecules at a single, defined point inside a 3-dimensional sample, producing images of living tissue at depths and resolutions impossible with conventional microscopy. Surgeons have used the same principle to ablate tissue with extraordinary precision, delivering enough combined energy to affect a single layer of cells without damaging adjacent layers. 2 photons, arriving together, can do what one alone cannot, and the boundary of what is possible moves with them. A light year is not a unit of time, it is a unit of distance. The distance light travels through a vacuum in 1 Julian year, approximately 9.46 trillion kilometers. The name contains the word year, and the concept bridges distance and time so seamlessly, because in this universe the two are not fully separable. Space and time are woven into a single fabric, space-time, in which motion through space affects the passage of time and vice versa. The speed of light is the conversion factor between them, the rate at which space trades into time and time into space. When you say that a star is 4 light-years away, you are saying something about distance, but you are also saying something about time, that the light carrying information about that star left it 4 years ago, and that you are seeing it as it was, not as it is. In the language of the universe, distance and time are the same conversation, and light is the word they share. Every shadow you have ever stood in was cast by an object that refused, for a moment, to let light pass. Every sunrise you have ever watched was the Earth turning its face back toward a star 93 million miles away. Every color you have ever seen was assembled fresh, at that instant, from the collision of light with matter and the particular way your nervous system chose to translate the result. Light is the oldest messenger in the universe. It was present before the first atom formed, before the first star ignited, in the earliest moments of everything, when the universe was nothing but energy moving through itself at the only speed the universe permits. It has been crossing the dark ever since. It carries no memory of the journey. It asks nothing of the space it crosses. It simply moves, at the speed the universe allows, delivering what it carries to whatever waits at the other end. And right now, in this moment, it is still moving, everywhere, all at once, as it always has. Set the facts aside now. Let them settle like dust in still air after a long day of gentle disturbance. You do not need to hold any of it. The light will continue without your attention. It always has. Right now, somewhere above the atmosphere, photons from the sun are arriving at the edge of space and beginning their descent through layers of air. Some of them will reach a sleeping city. Some will touch the surface of the ocean before anyone wakes to see them. Some will pass through a window and rest on the floor of a quiet room where no one is watching. The oldest light in the universe is still traveling. It has been traveling for 13.5 billion years, and tonight it continues, in every direction, through every corner of the cosmos, unhurried, unchanged, carrying the memory of a universe before stars. You are made, in part, of the same ancient processes that produce light. The atoms in your body were forged in stellar interiors, where light was born in tremendous quantities and pressed outward for thousands of years before escaping into space. You are not separate from what you have been listening to tonight. You are a later arrangement of the same old materials, resting now, in a darkness that is only temporary. The photons will return with morning. They always do. Your breath slows. The room is quiet. Somewhere outside, the sky holds its darkness gently, and the stars continue their patient, silent offering, sending their light toward a world that is mostly asleep. Let the unknown remain unknown tonight. It will still be there, vast and unhurried. When you wake, the questions do not need answers to be beautiful. The mysteries do not need solving to keep you safe. You are here. The light found you. That is enough. Rest now. Breathe. The universe is still. I hope you sleep well and dream softly. Good night.